Alright, so we mentioned that elements are defined by their numbers of protons. To be neutral, they have the same number of protons and electrons, but it ends up the neutrons can vary. And one of the earlier experiments people looked at were ionizing, in this case, a neon atom. So you strip off a couple of electrons or strip off an electron and run it through an electric field. And what happens is, as it goes through the electric field at a certain velocity, some of the ions are deflected more than the others. Even though they have the same charge, the same nuclear charge, this is because they have different masses. So it led people to understanding that atoms can have different numbers of neutrons by where they strike the in this case, the detector. What this led people to understand is for neon in particular, 90% of neon atoms have an atomic mass unit of 20, where 10% have a mass of 22 AMUs. So this led to the development of the theory of isotopes. Again, these are atoms containing the same number of protons, but different numbers of neutrons. So it's the same element, but the atoms have different masses due to the number of neutrons. Nuclide is a term for a specific isotope. To be honest, I just use isotope usually, but you see nuclide sometimes, so it's good to be familiar with the term. And this is a basic notation how we distinguish one isotope from another, one nuclide from another. Because they're the same element, we have to distinguish distinguish between the two. The X is the chemical symbol from the periodic table. It says it's one or two letter symbol. Remember that the first letter is always capitalized. People try to use lowercase sometimes, but to be proper, it's capitalized. The upper left number, they call atomic mass in this text. Normally, most texts that I've used, and I myself normally use mass number instead. To me, at least, atomic mass sounds more like it's saying this is the actual mass of that atom. And usually when I see people referring to atomic mass, they're talking about exactly how many grams or exactly precisely how many AMUs is that mass. This mass number is just the sum of the total number of nucleons in the nucleus, the sum of the protons and neutrons in the nucleus. So that's the mass number. It gives you an approximate mass of the atom, but it's not going to be precise. This will be an integer value, where the actual mass to decimals is going to be off by a little bit for a couple reasons we'll discuss later. One I'll mention is the electrons still are being ignored in the mass, in the mass number. And the lower left symbol that's used sometimes, the capital Z as a representation, is the atomic number. And this is often left off just because it's not necessary, but that's what the next slide is showing. So just said Z is the atomic number, A is the mass number, protons and neutrons. And this shows 4 different ways we can show the exact same isotope. This is the traditional way of writing it. You can see that in this case, the Z and the A are offset a bit just because with computer fonts it's hard to get them lined up precisely. But to be honest, we can look at the periodic table. If we know the element, we can look and determine what the atomic number is by looking on the periodic table. So that really isn't a necessary number. It's kind of redundant having that there and the chemical symbol. So in many cases, we just leave off the atomic number and just give the symbol with the mass number. From that, we can figure out everything we need. The mass number is used to figure out numbers of neutrons. We know protons because we know the element. This is, I'll go back there. So doesn't want to cooperate, sorry. Element name followed by A. You probably heard carbon 12 or carbon 14. Carbon 14 dating is radioactive carbon dating used to tell how old like mummies and tombs are, things like that. This method here, using the symbol and the mass number, isn't exactly considered proper, but it's used quite a bit. It's just an easier way to denote the isotope. So I use that sometimes myself. And it's used quite fairly commonly, even though it's not considered proper. So again, for carbon 12, it could be denoted like this, C12, or in all cases, we still say carbon 12. That's how we describe the isotope. Instead of saying 12-6 or something, we just say carbon 12 or carbon 14 or lead 208, whatever it is. So for isotope notation, to figure out isotopes, I'll go through a few examples of this to show you. We just use the basic format to write symbols for nuclide. In this case, for this example, use this format to write the symbol for the nuclide having 28 protons and 31 neutrons. So what we haven't discussed yet is the periodic table. Let me fast forward to one to show you. Sorry, should put one sooner. 28 protons. The periodic table mentioned in the next section is arranged by atomic number. You'll see up here, atomic number 1, go across a row, period, atomic number 2, 3, 4, 5, 6, and so on. And so you keep going, and this tells me how many protons that element has in its nucleus. So atomic number 28 is nickel. So all nickel atoms have 28 protons in their nuclei, no matter which isotope it is. So we go back here, and we have nickel, and we want to put the mass number up here at the top. That's the sum of protons and neutrons. So 28 plus 31, of course, gives you 59. So that will be the isotope notation for this nuclide. Let's go through a few more examples. I've got some over, let's see. All right, let's go through a few other examples. Well, I'll show you carbon 12 again. Get my pen back. There it is. Carbon 12, protons 6, electrons has to be 6 so that it's neutral. Neutrons, of course, 6. Versus, say, carbon 14, still has to have 6 protons because it is still carbon. All carbons have 6 protons. Therefore, it has to have 6 electrons since it is electrically neutral. And neutrons, of course, sums of neutrons and protons gives you the mass number. Again, that's what the mass number is. So therefore, it must have 8 neutrons. Something like, let's say, sodium, I'll write this way instead, sodium 24. Look in the periodic table, you'll find sodium has atomic number of 11, which means it has 11 protons. Since it's a neutral atom, it has to have 11 electrons also, and therefore it has to have 13 neutrons. So if we take something like an H2 isotope, which is called deuterium, hydrogen has 1 proton, therefore 1 electron, also has 1 neutron. Now on the other hand, if we take what's called the protium isotope, which is H1, 1 proton, 1 electron, but this has 0 neutrons, the only stable isotope, naturally occurring isotope that has no neutrons at all. And that's the most common isotope for hydrogen in addition. So pretty straightforward. We should spend a minute discussing ions also. It's in the text here. So then I'll go back to the next slide where I think the book is a little bit misleading there. Let's look at, let's just take, I'll take an oxygen atom. Let's take oxygen 18. Looking in the periodic table, it's got 8 protons. Also has 8 electrons, therefore it has 10 neutrons. Now if we were to take an oxygen ion, let's take, the charge is shown in the upper right corner, and it's usually shown as a 2- versus a -2. I'm not that picky of this course, but for right now, but to be proper it should be a 2-. So this is still an oxygen atom. Well, it's technically an ion now, but it has 8 protons. That won't change any. We'll get to electrons last. Let's look at neutrons. Again, this is based on an oxygen 18 isotope, so it still has 10 neutrons. Electrons is where people get tripped up. Part of it is because this is a -2. We tend to think when you have a negative, that means you're taking things away. Well, remember that electrons have negative charges, so if you add negative charges, our charge gets lower. So that means that this oxygen has 2 more electrons than it has protons. Therefore, it must have 10 electrons. In fact, this is what happens whenever chemicals bond, whenever atoms bond to form compounds in chemical reactions. They gain or lose electrons. The nucleus is in the center of the atom. It's very stable. It doesn't split apart unless you have some nuclear reaction going on, which is really rare. and the electrons are on the outside, and that's what atoms encounter when they come near each other. So all chemical reactions deal with electrons being gained or lost. So never change protons, only change electrons when you have a chemical reaction occurring. Now to double check this is really simple. We can say we have 8 protons, we have 8 plus 1 charges plus 10 electrons, or 10 negative 1 charges. Of course, this adds up to 8 minus 10, which equals negative 2, which should be the same as our charge over here, and it is. So that's a good way to confirm that we've done the charge correctly. And then people try to say, well, if I've got a negative charge, I'll add 2 electrons, or I'll take 2 away. They try to memorize, take 2, add, take 2 away, add 2. When we get to electronic configurations, and you might go from configurations to symbols, or symbols to configurations, that gets confusing. So I always try to reinforce, go back to what the charge really means. It means we have more electrons than protons, so you always use that to double check yourself. Just save some careless mistakes and save some headaches. If we take something like, let's just take a sodium ion. Oh, find out where my pen went to. Sodium 22, for example. Well, this has, the atom has 11 protons, so it must have 11 electrons. In this case, this will have 11 neutrons. But if we take a sodium ion, let's say a sodium 22 ion, it forms actually usually a 1 plus ion. It still has to have 11 protons. It still has same isotope basis, so same number of neutrons. But now the electrons have changed. It has a plus 1 charge. And again, we think about plus, we think must have added something to it, but remember that the charge just shows us we have more protons than electrons. But we can't change protons, so that means that we must have lost electrons, so we only have 10 electrons. We can double check that. 11 protons, we still have 11 plus 1 charges, plus 10 electrons, so 10 negative 1 charges. 11 minus 10 gives us 1, so that's the same as our charge. So it works out fine. We could say, we could find the isotope if we have an isotope that has, say, 17 protons, 17 neutrons, and let's say 18 electrons. So we'll look at a periodic table. This might be good to do yourself first. Pause the video, look it up yourself, and come back here. Alright, so if you've done that, atomic number 17, hopefully you saw that this is chlorine. Mass number is sum of protons and neutrons. And in this case, I put protons and neutrons side by side. Up here, protons and electrons, the neutrons on the end. Really did that on purpose to a point was people get in the habit of, take the first number goes here, second number goes here, third number goes there. We don't always have them in the same order. So make sure, just pay attention to which particle is being given, because it's easy to make careless mistakes. So just a few things like this to try to keep you on your toes, just to make sure you don't get into habits of just sticking numbers in without thinking about them. So 17 plus 17 gives us a grand total of 34 nucleons, so our mass number is 34. We have 18 electrons, 17 protons, so we must have a charge of -1, or to be proper, we put 1 minus. If we have something like, say, 12 protons, 10 electrons, and 14 neutrons, well, look at our periodic table. Atomic number 12, that's going to be magnesium. So we have Mg. Our mass number is protons plus neutrons over here this time, so that gives us a mass number of 26. Our charge, we have plus 12 minus 10, gives us a 2 plus charge, and that's it. That's all we need. So let's look at a few of these examples. In the text it does this, and be careful of things like this. This actually is kind of improper. The way they set this table up, I sort of left this to describe this for you. It says identify atoms and ions. Well, in this example there can be no ions, because if there are ions you cannot solve most of these problems. To know whether it's an ion, you have to know either the charge or be given protons and electrons. Only in this first example does it tell you the charge. So without having protons and electrons, you have to assume everything here is going to be electrically neutral. So number of protons, look up a sodium atom. It's going to be, actually you could do this first yourself. Fill this in, pause the video, and then come back. It'll be a good idea for you. Now that you've done that, number of protons, of course, should be 11 here. Number of neutrons, well, 23 minus 11 gives us 12. Number of electrons is neutral, so it should be the same as protons, so 11. Mass number is actually up here already. Sum of protons and neutrons, so it's 23. So for the next column, if you haven't figured out this yet, if you got stuck there, 39 is the atomic number of protons. Look in the periodic table. That gives you, get my periodic table out here, a little small print. Yttrium. So symbol Y. Neutrons we have, electrons needs to still be 39 since it's a neutral atom. Mass number will be, sorry, it looks like a 4 there, it should be a 9. If you'll let me draw it. Oh, there it goes. That's a better 9. Alright, so neutrons 50 plus 39. I'm sorry, 39 plus 50 gives me 89, which is also what we need to put up here to complete our isotope notation. Sorry, this pen doesn't draw very well in here. And now we get to the third column. Number of electrons is 50, so our protons must also be 50. Except my pen's not willing to work very well. And that means atomic number 50 is going to be, that's 10. And we already know the mass number is 118. Number of neutrons will just be mass number minus protons, so 118 minus 50, which should be 68. And last column, atomic number 79. Oh, that's gold. We already know the mass number, 197, should be up here. Neutrons, so 197 minus 79 should be, is that 118. And electrons, of course, will be 79, just like protons. And that's it. So it gives you a basis of isotopes and isotope notation and a bit more familiarity with ions.